Good day, everyone. So, another topic for our final video discussion is about differentiability and total differential. So, for functions of several variables, differentiability extends the concept of local linear approximation from single variable calculus. A differentiable function can be approximated by a linear function near a point, and the total differential provides the best linear approximation to the change in the function's value. So in this video, we will gonna aim for this outcome. So we are going to identify and define differentiability for functions of two or more variables, and we can compute the total differential of multivariable function, use differential to approximate changes in function values, and understand the relationship between partial derivatives and differentiability. So let's start with our lesson. So we have here a definition for our differentiability and total differential lesson. So for the definition, if z is equals to f of xy, then f is differentiable at a and b. So if the change of z can be expressed in the form change of z is equals to f of x ab, change of x plus f of y ab, change of y multiplied to the change of y plus the epsilon sub 1 multiplied to a, the change of x, and the plus the epsilon 2 multiplied to the change of y, where epsilon 1 and epsilon 2 is approaching to 0 as the change of x and the change of y approaches to 0 and 0. So according to the definition, a multivariable function is considered differentiable at a point if the linear approximation or the tangent plane to its graph at that point closely matches the actual function for nearby points. So in practical terms, this means that when you zoom in sufficiently at the point of tangency, the graph and the tangent plane becomes virtually indistinguishable. However, applying the definition directly to check for the differentiability can be cumbersome. So it does not apply always that you are directly applying the definition. So we also have here a theorem. So if the theorem says that if the partial derivative of f sub x and f of y exists near AB and are continuous at A, B, then f is differentiable at A and B. So this means for this reason, this theorem provides a more convenient and widely used sufficient condition. So if a function partial derivative exists and are continuous around the point, then the function is guaranteed to be differentiable there. So simplifying the verification process significantly. So let's have our first example. So compute the differential dz for z is equals to x cubed y squared plus 2y cosine x. So for our solution, we simply have f of x or f sub x is equals to 3x squared y squared. Because it is multiplication, we cannot serve the y as a constant because it is a multiplication. In case that it is subtraction or addition, we can serve the y as a constant, but in this case it cannot. So we have 3x squared y squared minus 2y sine for with respect to x. So for our f sub y, we also have 2x cubed y with respect to y plus 2 cosine x. So the dz here is simply substitute it 3x squared y squared minus 2y sine multiplied to dx because it is with respect to x plus 2 2x cubed y plus 2 cosine x multiplied to dy as it is with respect to y. So that's our first example. For our second example, it is kind of different because it has a decimal, but let's see how we will solve it in the topic of differentiability and total differential. So for our example 2 and the last, we have used differentials to approximate square root of 3.02 squared plus 3.99 squared. So the solution, we need to let f of x and y is equals to square root of x squared plus y squared, where x becomes 3 and y becomes 4. And our dx is equals to 0.02 and our dy is equals to negative 0.01. So we have now f sub x is equals to x over square root of x squared plus y squared, and our f sub y is equals to y over square root of x squared plus y squared. So at 3 and 4, our f sub x is equals to 3/5, and for our f of sub y is equals to 4/5, and for our f of 3, 4 is equals to 5. So the change of z is approximately equal to dz, which is equals to f sub x dx plus f sub y dy is equals to 3 over 5 times 0.02 as the dx earlier plus 4 over 5 and times negative 0.01 as our dy earlier. So we have now 0.012 minus 0.008 is equals to 0.004. So thus, our f of 3.02 and 3.99 based on our problem is approximately equal to 5 plus 0.004 or equal to 5.004. But we have here the exact value of our problem, which is square root of 3.02 squared plus 3.99 squared is approximately equal to 5.00399. And that would be all. Thank you. God bless us all.